Okay. It's Friday. It's kind of miserable outside. I vote we get through what we need to do quickly and everyone can get to their weekend faster. So you can move back. I know what I want to do is go back home and sleep. So you guys, I hope you can do whatever you want to be doing this day. Why do I even bother with that? So, when we last left off, we were talking about, I mean, I've had a couple of lectures since then. We're talking about Ohm's law, V equals IR. Okay. Today we're going to further expand upon what it is that physically makes a resistor, and hopefully, if we don't get to it today, it's okay. My goal, my light, is that we can at least start talking about electrical power, and specifically how we can use it to calculate your electric bills. So does anyone have any questions before we get started today? I did upload more complete notes for this chapter on Brightspace. Now you guys get to watch me embarrass myself by jumping. Okay. That was better than I thought it would go, frankly. Okay. So we've glanced at all this information before, correct? So we've talked about V equals IR. It's very important because it defines pretty much all of the interactions going on inside of the circuit in terms of how it normally functions. Now, there's another formula on here that I'd like us to expand upon a little bit further. I believe we at least talked about all the terms in this formula. Resistance. Every single object would have some electrical resistance, and that resistance is affected by what it's made of, its length, and its cross-sectional surface area. Today we're going to actually do a little bit of that math, and to further expand upon the formula. Aiming for the trash can, sorry. Not about as well as I would expect it to. Thank you, sorry. So, resistance is vectored by resistivity constant times the object's length times its cross-sectional surface area. I know that we keep reusing rho for different things. Ran out of good letters a long time ago. Between the main two alphabets used in the Western world. Now, that rho is important because it defines the electrical properties of the substance that the object is made of. And this is true for not just machines, but also the stuff you plug into the circuit, which includes the wires. The wires, the batteries themselves all have some amount of resistance technically because they're made of some material, they have some length, and they have some cross-sectional area. So every single thing has a resistance. What it is just depends on these variables. There's one variable that's not in this formula though because it's in the sister formula, and that's temperature. At least mentioned that the hotter something is, the worse it conducts. The more things things resist more when they're hotter. And how we factor that in is through this resistivity constant. So I'm going to start labeling all of these terms. Rho is resistivity constant, and it is affected by physically what the object is made of, but also by temperature. And we have a separate formula, as shown on screen now, how temperature affects this specific number. Now, through a lot of experimentation, the scientists the material scientists who analyze all the things in the universe, determine their physical properties, through a lot of experimentation, these people have figured out two more constants for every single material that we use to build things out of. The first is the sort of baseline resistivity at an established temperature. So this is resistivity prime at a prime temperature. And we adjust resistivity based on changes from that temperature. I'm going to show you the table that has all these constants on it just to give you an idea of what we're working with. The first column here for every material is its baseline resistivity at 20 degrees Celsius. So if all these materials were at 20 degrees Celsius, this is the Rho constant that you could then plug straight into here. This is Rho prime defined at 20 degrees Celsius. If we change from 20 degrees Celsius at all, then we have to adjust that value by a certain amount. And that amount changes based on the temperature change and also based on the specific material. So every material up here also has an alpha constant. In the formula, that alpha is what we multiply the temperature change by to offset Rho prime to whatever Rho should be at this current temperature. Then the formula. This is the resistivity constant at whatever your system's temperature is. We've also got base resistivity at 20 degrees, and we have adjustment value. So looking at this formula, if T base is 20 degrees and we are currently at 20 degrees, what happens to this whole term?
0.
This whole piece here becomes 0, which means the entire brackets can be compressed to just 1 and then times the original, which just shows that if you're at the temperature set by this starting Rho, this whole thing falls away and you're just left with the initial Rho. It's only when we are adjusted from there that it starts to change. And frankly, because these two formulas just go hand in hand, I tend to end up writing them as one combined formula more often than not, which, go ahead and take this up for the work we're going to do in a second.
So do they like never give you it at 20 degrees?
They do. We're gonna start with 120 degrees. But if it is at 20 degrees, the whole alpha term just goes away quickly. So we're going to need it combined like this fairly frequently, so I tend to just leave them combined. So as an example, let's say that someone is building a resistor out of tungsten, which I think is actually a pretty bad idea, because I think tungsten is one of the more conductive things on planet Earth. If you want it to resist, you might not want to make it tungsten. And for the sake of simplicity and ease of calculating, let's assume this particular resistor is just a brick, basically a very tiny stick of butter made out of tungsten, and it would have the legs coming out of either side. But it being this shape makes our calculating just a little bit easier. We know it's made of tungsten, and we know its dimensions. I specified that it is 3.25 centimeters long, and that the sides, or rather the cross-sectional surface area, is defined by 0.01 millimeters and 0.01 millimeters.
What is, W is tungsten.
Yes, and I'm always shaky about my own memory when I try to do, when I assume that that's the case. I can only remember it because it wasn't until I was teaching chemistry to like freshman high schoolers that someone finally told me the reason the letters on the periodic table are what they are is because of Latin. And I can only remember tungsten as W because for some reason I remember its Latin as wolfram.
Say it again?
Wolfram. I'm assuming it's wolfram rather than wolfram. Yeah, tungsten is wolfram. I'm sure the Latin definition is a lot less interesting than wolf plus ram. Now, the reasons why I can remember that aside, since we know what this thing is made of, we can look up its resistivity constants. So, with tungsten, its base resistivity at 20 degrees Celsius is 5.6 times 10 to the negative 8. That number does technically have units. That's ohms times meters. And the temperature coefficient, the adjustment value for tungsten is 4.5 times 10 to the negative 3. That's 3. And that's in units of 1 over Celsius, I think. Yes, it is. Okay, so we have resistivity initial for tungsten and temperature coefficient for tungsten. I'll further define at 20 degrees Celsius. With just those constants and the information given to us about its physical dimensions, can we find the resistor's resistance at 20 degrees?
Yes.
Yes. So at 20 degrees, what happens to this whole piece? 0. So we'll just skip that part for right now. So R at 20 degrees Celsius will be equal to rho prime at 20 degrees, so 5.6 times 10 to the negative 8 times 1, because the alpha term goes away. Then multiply by the length. Length is given as 3.25 centimeters. We do want meters, so that's going to become 0.0325. And then we need cross-sectional surface area. We're given millimeters for the two axes that determine that. And I prefer converting things into meters before squaring them as opposed to after. And thankfully, the two sides that aren't the length are the same. So they're both 0.01 millimeters. So those should convert to 0.00001 meters.
4, right?
Yes, 4. Because there was 1 initially, you'll need to add 3 more when converting the base. And since it's the same number of times itself, we can just write that as squared. So, when you plug that into our calculator, let me know what kind of numbers you get together. Just to go ahead and set your minds at ease, it's going to be not like smaller than 1 small, but comparatively small.
18.2.
18.2. And what is the unit for resistance?
Oh, yeah.
Ohms, yes. Omega. All right. So that is the size of this particular resistor at this temperature. If we were to take this particular resistor and plug it into a 120 volt battery, what then would be the amount of electrical current flowing through it?
V equals IR.
Correct. We can do V equals IR, plugging in 120 volts, solve for current, times 18.2, and we are going to get a number that, electrically speaking, is irresponsibly large.
6.59.
And you remember what I said about how current is dangerous and we keep it small on purpose? After talking about that with my other lecture, I actually looked up the numbers. And while any amount of current can be dangerous if it is applied to you for a long enough period of time, 1 milliamp is enough to cause pain. 0.1 amps can kill a human. This is over 60 times larger. So this, if this situation happened, it would need to be in a highly controlled industrial environment where high current is needed to run some super machine. I wouldn't want to be anywhere near this. But the current's not going to stay there forever. Because as soon as you plug this thing in, electrons are going to start surging through it at a very fast speed. Its current is functionally the electricity's speed as well. It's not just, you could think of it as number of electrons passing, but you could also think of it as a lot of them are passing very quickly in a short amount of time. Either way you look at it, that's a lot of current, and that current is carrying a lot of energy. And when current travels through anything, it tends to warm up pretty fast. As soon as you turn on your laptop, it begins heating up and the fan kicks on to keep it cool. When electricity runs through anything, it gets hotter because by virtue of resisting the current, you take energy away from the electricity. And that energy is now in your atoms, making them hotter. And this is why when people are struck by lightning, the injuries are usually burns on the inside of you.
Not outside?
I mean, your outside gets kind of steamed too, but the current is mostly passing through your highly conductive inner tissues. So occasionally some of the water in your blood starts to boil. And that's why most of the scarring for lightning strikes happens beneath the skin. So, we plug this in, it's going to start getting hot very, very fast. Same as a light bulb. It's going to warm up to approximately 3,000 Kelvin, which is also irresponsible. So I don't know who's running this lab. First question is, at that new elevated temperature, what is the resistance going to change to?
And we said, the T. Oh, it doesn't matter because, it can be in Celsius or Kelvin because it's.
Yes, you can use either as long as the two temperatures you plug in are the same unit. Because since it's T minus T initial, this is basically a delta T. As long as it's delta T, you can use Celsius or Kelvin. Those will cancel out, those units will cancel because they are the same size. So you could write this as 1 over Kelvin if you wanted to, it wouldn't change anything. So at 3,000 K, which is probably hot enough to make the air glow, now that we have changed temperature, we do need to factor in alpha. We said the alpha for tungsten is 4.5 times 10 to the third. I'm going to multiply that. You know, I need to compress this slightly. I'm running out of board space.
That means we need to be 20 degrees Celsius and
Sorry, say that again?
we need to make 20 degrees Celsius and Kelvin.
Yes, we do. I apologize for my horrendous board spacing and note-taking today. So what we have here, I'm going to say it out loud since it's kind of mangled by the intersection between boards. We took our formula, we started plugging things into it. We've got our row initial, 5.6 times 10 to the negative 8th, times everything in our brackets, 1 plus alpha. Alpha is being multiplied by the change in temperature. We were given Kelvin for the new higher temperature. So I changed the starting temperature into Kelvin. And 20 plus 273 is 293. Please correct me if I'm wrong. Close that whole set of parentheses and then multiply everything so far by the same L over area, because that hasn't changed. So by increasing the temperature by a factor of nearly 3,000, the resistance has increased by a factor of like at least 12 times bigger. Which, this number in the grand scheme of things is still not very large for a resistor. Most machines have a higher resistance than that. The human body, at least human skin, has a resistance of 100,000 ohms. So this is still not very big, but it is noticeably bigger than where we started. And that can cause problems in any sort of industrial electrical environment. Because what's going to happen to the current inside the machine when this happens? We perform the same operation. We're just going to take our new higher resistance and plug it in instead of 18.2. So what does that make the current at 30,000 Kelvin? 0.5 amps. Actually, the answer was up there, I'm sorry. It's not a spoiler. Sorry, this isn't a surprise. So that current dropped by about a factor of 12. And again, this is still a lot. This will still kill a person. But if the machine, if the system needed that much current, we've hit meltdown territory. Everything is hot, so things are probably melting. There's not enough current to keep the system on. It would have shut off if you're lucky. It would have melted if you're not lucky. Any questions? Okay. I would like, we're nearing the end, and I don't want to start too much on Friday at this point, but I do at least want to introduce the formulas for power to you, which, well, you've seen these actually in lab this week. I just like to talk a little more about them. Because we're not going to get through everything I'd like to talk about, I'm going to make the homework due next Thursday, so that we can formally wrap things up on Tuesday and have time for questions on Thursday. Just because I don't think we have time to talk about how electric fields are calculated, it's not comfortably. So, every single thing in a circuit is taking energy away from the current. Current comes out of the battery, runs through the wire. When it hits the resistor resists by literally taking energy away from it. And you know what, something I haven't actually mentioned yet. Yeah, there's another point about resistance I need to make before I get too far into power. I apologize. Electricity, technically speaking, is lazy. Let's say we have set up here a parallel circuit. One branch is 1,000 ohms, one branch is 10 ohms. Electricity is lazy in that it will literally pursue the path of least resistance. It will take a pathway between the 2 points it wants to be that involves the least amount of work, that involves losing the least amount of energy. So in this circuit, the current is going to come to this junction and some of it is going to go in both directions. Which direction do you think is going to have more of it? The path of literal lower resistance. So, for your notes, electricity. You know what? I should just make a slide of this on it. Writing it out is no faster than me typing it. always takes the path of least resistance. This is why rubber insulated wires protect us. Have you ever, as a child, or even as an adult, because this is still a valid question, noticed birds sitting on power lines and wondered why they're not getting shocked? And how do they do that? Very weird pigeon. If you've ever at any point looked at this and wondered why, you're not alone. And the reason why is because of that rule. The wires themselves, they're coated in rubber, and the nice conductive middle part is made of metal. The metal has a much lower resistance than the rubber lining the wires. And thankfully for the bird, it's a lot of effort, too much effort, for the currents to bother exiting the rubber to use the bird as a parallel circuit. Because the electricity wants to get from the power plant over here to your house over there. It would make no sense for it to take a detour through the bird, because that's slower pathway to get to the house. When you install a bird like this, you would be basically making a parallel circuit. You've got a split between the metal wire and a split between the bird. But because of the rubber's resistance, the electricity has no reason to do so. It's just easier for it to stay in the wire. But even if the wire wasn't rubber coated, the bird might still be fine, because it would still be easier for the current to stay in the metal than to detour into the bird. Because it's just going to exit the bird through its other foot, because it has to form a complete circuit. It's just going to exit through the other foot and then keep going. It's dangerous without the rubber, but in the right situation, you could still be fine. Additionally, if a person was just hanging from this power line by one hand with no foot touching the ground, they would probably still be okay. Because it's not worth it for the current to enter the human, circle the human, come back out of the human, then go into wire.
Why one hand?
Because if you, well, for one, if you had the other hand up there, you do create a parallel circuit, and some of the electricity might still try to enter your body, because even if this is the lower path, some will still go this way. So it's risky if you're hanging from both hands, but not as dangerous as if you had both or one of your feet touching the ground. Because even though the electricity really wants to go to the house down the street, the place it wants to go even more is the earth. Because the earth has even lower electrical potential than your house. And we're always going from high potential to lowest potential. So touching a line and standing on the ground is a surefire way to get shocked. Because now least resistance doesn't matter anymore. The current wants to be in the earth really desperately. So it's going to try and do it. Yes?
Is that why when like power lines get like knocked down, like from a wreck, like if you're in the car, just to stay in the car instead of getting out?
Yes, that is an excellent point. If for some reason a live power line is touching the metal of your car, or your car gets struck by lightning, as long as you are inside of the metal car and not touching the metal, you'll be safe for as long as you stay there. Because for the metal of the car, the electricity has entered the metal. It would much rather be in the highly conductive metal than anything else. So as long as you're not touching that metal, it shouldn't bother trying to enter you. The problem is that your car probably has rubber tires. which means that that electricity that is now trapped inside of the metal of your car doesn't have a good way to get into the earth because it can't really conduct through the tires, not easily at least. So the electricity in your car is going to take a pretty long time to discharge and leave your car. As long as you're not touching the metal, you'll be safe. Because it's just trying to go from the metal into the earth. It's not trying to go into you. But it does effectively mean that you're just going to be kind of stuck in there for a while. So the professional advice for I'm in a car that has been struck by lightning or there's a power cable touching it is stay in the car until someone arrives and you know for certain that the car is discharged. If you have to get out because it's a storm and something bad is about to happen to it, what you would want to do is only touching like the plastic inside of the car. You want to open the door fully and then jump out of the car. You want to jump and be in midair, no part of you touching the car, and then both your feet land on the ground at the same time without touching the car. Yes, thankfully the odds of you being in a car struck with lightning are very slim. The main thing to remember is you're safe in here. You only need to worry about opening the door and being gymnastic if you really need to leave. So, just in case it has least resistance, it's lazy, rubber wires are good, because it means that it's just too much effort for the electricity to exit the wire and enter us. Also, don't hang for power lines. Okay, we're about at the end. I don't want to keep you guys too long. We're going to start next time talking about electrical power, because when anything has electricity running through it, by virtue of resisting that electricity, you are taking energy away from the current. The reason we have voltage drops across resistors is because the resistor eats energy out of the current, and now that it's lower energy on the other side, it has lower potential. So the voltage drops across it, literally. And because you are draining energy, and we can measure the amount of time in which you drain that energy, each device, each thing plugged into the circuit is using up a specific amount of electrical power. And this is the same power that you've been using in every physics class so far. It's still energy over time. It's still watts. I'm actually under the impression most people hear the unit watts and automatically think electricity. And it's because we bill, in like all of our electrical systems in the US are billed based on kilowatt hours. So the unit itself is generic for all power, but it's attached to electricity in our minds, and now we're actually going to use it as such. So next Tuesday, we'll touch back on the formulas for electrical power, and I will teach you how you can use that to figure out your electrical bills, and help you at least show you why they are what they are and how they are calculated. Any questions? Okay. Let me know if you have any questions. Homework and quiz are now going to be due next Thursday, so I'll be working on those. That's the chapter 17 homework and quiz. These notes are already online. Send any questions you have, and you have a wonderful day. Have a good kid. Stay safe and dry and healthy. Not tornadoes.